Welcome back to physical chemistry, or welcome to physical chemistry. This time I'm going to try it a slightly different way to how I normally do it. So I'd like to think about all the ways that light can interact with molecules, with chemicals to start with. So if we take a molecule, let's take the absolute most simple version, it would be an argon atom. An argon atom cannot do very much. It can move in different directions, so it can go up, down, left or right, but it doesn't have any bonds, so the bonds can't do anything. It can't rotate, because if we imagine it's got some kind of orbitals that are sticking out, if it rotated, because the electrons are free to exchange and do all kinds of things, we can't actually tell whether it's rotated or not. Unless there's something attached to it, it makes no difference. So there is no way to tell whether an argon atom is rotating or not. We could tell if the core is rotating, because it would have rotational energy. So that might be one of the things that we could put energy into. So effectively, let's try and draw it as a Bohr model. So we can put our energy here into the core, and we can put it into the electrons. Those are our two possibilities for our argon atom. If we think about what else we could do, we could make it move faster. So those are the directions that would be warming it up effectively. We could make it move faster, but we have to interact with it to be able to do that. Whoops. And that's kind of difficult. So how are we going to heat up this argon? We need to be able to get the energy into it, and that, we could give it some translational energy. That will be, it's possible, but it's difficult to do it with light. If we go up to a slightly more complicated molecule, a diatomic molecule, it doesn't have a charge because it doesn't have a dipole because it's two hydrogens. We can give it energy too. We can make it translate. That would make it warmer. It's difficult with light, just as argon is, but we could excite the bond in addition, and as an extra additional feature, this molecule can rotate. So if we move this hydrogen down and this one up, or this one to the side and that one to the side, we get rotational kinetic energy, and we can excite that with light. That's done at the very long infrared, but it's possible to excite molecules with light to rotate. Usually we would excite a vibrational band as well. So in this case, there's only one possibility. This bond can stretch and shrink, and that gives us our movement. And we can give it more energy. That movement is quantized, so maybe we should look at that first before we get more complicated. So if you've been doing normal physics with our normal physics people, you will know that if we have a spring with a weight on one end and it's doing nothing, it will have a squared form of curve, because as we compress it, the spring force goes up linearly, and so the energy goes up quadratically. So we go, as we compress it, we get more and more energy. The force goes up. We get, so this should be E and not F. And we end up going up here. As we stretch it, it gets longer, and a perfect spring is completely linear, so it goes up in the other direction. So that all works nicely. That would be a perfect system. And if we had a spring that was perfect, and we started here, and we springed it, it would oscillate between these 2 points. And if we had a spring that was here, it would oscillate perfectly. And it's a macroscopic spring, so we don't expect it to be quantized. So it will be, we can stretch it to any point on here and let it go, and it will oscillate between these two. And in the wild, or in the intellectual world of physics, where we can imagine that there's no friction and nothing bad happens, it would do that forever, because we like to simplify things. The good thing about molecules is they are simple and they would oscillate forever if nothing happened. The bad things about them is they're not perfect oscillators. And also the other bad thing is they're quantized. So this is our hydrogen, and we want to think about what it really should look like if we approach from one to the other. Let's call this delta E, because we don't really want to worry about where zero is. It kind of becomes a problem. So let's use the change in energy. It makes it better. It's better defined. So this is our hydrogen. There are 2 electrons in it. They're both somewhere between the 2 hydrogen atoms, somewhere between the nuclei. And we want to vary the distance, which we were calling r here. It's often called r in molecules, so for radius. If we stretch it, so we have our dotted on parabolic curve, which would be a simple case, and we want to know how is it going to differ. Well, as we stretch this apart, we can imagine that there will be a distance where they don't interact anymore. So as we stretch it apart, it will get unhappier and unhappier, and then really it's not going to interact very much, because at some point this bond will break and they will become 2 hydrogen atoms like this, H dot, and the hydrogen atom will attract the other one. Either one will end up with both electrons, or they'll have one each, but it doesn't make a massive amount of difference. It's slightly worse in this case because there's no reason for them to attract each other apart from this formation of a bond, and the bond can't be infinitely long because we would then have to have an orbital that was infinitely long. So we can imagine that this isn't going to go on forever. At some point it's going to turn over and do something else. It's going to turn over and we're going to get no attraction. There's no reason why it should repel, so it's not going to go back down again. And there's no reason why it should attract more if they're really, really far away. So we can imagine that this is going to now go flat and carry on forever. As we get to the bonding size, we're going to get some kind of hole, but if we get closer, we can imagine there will also be a problem, because we can't get closer and closer and push it to 0, because then our 2 atoms will be on top of each other. So something weird has to happen there. If our 2 atoms are on top of each other, we have our exclusion principle. We would like to say, so it's Pauli's exclusion principle, we would like to say the 2 particles, the quantum mechanical particles, are not allowed to be on top of each other. We don't have a great explanation for that at this point, but we can hand-wavingly say, okay, well that can mean that this side of the curve is much steeper than our quadratic curve, than our normal spring would expect. So I'm going to rub those out so that I can draw it in. So then we would get a curve looking more like this. It's usually shifted a bit to the left, but let's not worry about that. So now we have to think about what the atoms are doing. We've got a curve, and our atoms is 2 hydrogen atoms. So this is the distance between the 2 hydrogen atoms. They're not there. One of them is here, and the other one is over here. So what they're doing is this one is going this close and this far away. It's the distance, and it doesn't tell us which one of them is moving. So there, I can't do it because I haven't got the technology right now. We will get better technology when it arrives. So we've got a bond that's getting shorter and longer, and we're only measuring the movement of one of them. We're imagining one to be fixed because we're just using it as our 0 point. So this is the distance between the 2. It gets longer and shorter, and it can't be 0 because we know they would be on top of each other and we would end up with a neutron star. That's obviously possible, but we also know that doesn't happen when you heat up hydrogen gas normally. It doesn't happen when you cool down hydrogen gas normally. So we're not going to accidentally make a neutron star. Special things have to happen for that to occur. If we've got this going on, so we've got, oh sorry, I've rubbed out my hydrogen. So this is my hydrogen here, and this is the other hydrogen, and it's moving between these 2 points because we've got that amount of energy, whatever that is. If we now heat up our hydrogen, we have a quantized amount of energy we can put into this bond, and then we can heat it up to the first excited state, for example. That is possible. We can do that, that's not so hard. And then we can heat it up to the second excited state, and you can see here that there's a problem. Because our curve is not symmetrical, the gaps between these are not going to always be the same. So these tend to get closer and closer together as we go up, partly because the distance, the length of this is getting unusually long as we get further up because this side is open. If we heat it up too much, we can see that we would predict that our molecule, our hydrogen molecule, would fall apart, and that's good because we know that happens. We know that in our sun it's very hot and there is no hydrogen as H2. It's all present as hydrogen atoms, and in fact in most of the regions of the sun it's not even present as hydrogen atoms. The electron and the nucleus leave company of each other. It's so hot that they are up here and just don't have any connection with each other at all. But in our normal world, in most normal temperatures, we don't have quite so much, so we can heat it up so that it can break, get a plasma of just hydrogen atoms, but most of the time we're down here where we can form molecules. So this is another way of describing molecules. We know several ways of describing molecules by now. We could use orbitals, we can use energies, we can use thermodynamics, we can use kinetics, but all of them should describe the same real world. We should be able to get from one of them to another, or at least know when one of our models gives up being useful and when another one becomes useful. So as we might have had in chemistry, I'm not sure, as you might have had in inorganic chemistry, the model used very predominantly for Lewis bases and Lewis acids, the electron model, the valency model for chemistry works pretty well for a lot of chemicals, and then certain cases it just doesn't describe very well, and the orbital model is very much better. If we get here, we have the same thing. If we want to be describing transitions caused by light or heat, this is quite a handy model. And if we want to describe transitions by light, we almost need this model because other ones don't work. We will have to make our model a little bit better before we do that. So at the moment, we've just got a vibration of this bond, and how are we going to cause that vibration? Whoops, sorry about that. How are we going to cause that vibration? Well, we could put in some light, and that would be typically infrared. And the infrared will cause this bond to vibrate. So in this case, the only thing that it can do is get longer and shorter, and it's getting more energy, so it's sort of pumping faster and harder further. And what that means is if our hydrogen molecule finds another hydrogen molecule that's in the lowest energy state, it could interact with it, that this hydrogen here that's moving punches it and makes it move faster, which could mean that our energy is then turned into translational energy, which we know of as heat, or it could turn into vibrational energy in the other molecule. So what happens when we heat this thing? We had our argon. If we heat it up, we could put our energy, our heat energy, into it, and really there wasn't a whole lot of choice. It could go into the electrons, but we need a lot of energy to do that, or it can go straight into translation, which we can do by heating relatively easily, because if we're heating it up, what are we really doing? We've got a container that we've made hot, and the heat is getting into our gas, because argon's usually a gas or liquid. And what's effectively happening is the oscillation, the vibration of the walls of our container, because it's hot, are punching the molecules and making them go faster. atoms of argon. If we have light, it's quite difficult to do that. As I said, if we've got light here, we can excite a vibration in our hydrogen and use the vibration, the decay of the vibration, to cause the hydrogen to get hotter. So if we put light in, we can convert it into heat easier if we have hydrogen than if we have argon, although there are some rules that makes it difficult even in that case. So if we take the specific heat capacity of a material, let us consider argon to start with. Its useful property is that it's basically flat with, oops, sorry, that was a shitty flat, but it's basically flat with temperature. So this is, oh, let's put T here. C, T, yeah, E and T are the same, E, T. It becomes a problem in the next stage. So if it's completely flat, obviously energy and temperature are the same thing because nothing happens. If we put more energy in, it gets hotter, and we know that from heating up water. So our common physics rule of thumb is it takes a certain amount of energy to heat up water by a degree centigrade, and that's our definition for units of heat. But what we want to know is what happens when we have a molecule that is more complicated and when we get exciting things happen, because then we can make some predictions. So in our water, complicated things are happening. Some of that energy that we're heating it is going into vibration of the bonds, and some of it is going into rotation of the molecules. And we don't really know, because in our world and our normal temperatures, all of that is going on all of the time. But what if we reduce the temperature down to a very low temperature and we use something a little bit simpler like hydrogen? So this would be argon, where nothing happens. Okay, there's a phase transition in there somewhere where the argon will liquefy. So at some temperature it will liquefy and go weird. But let's not think about that just now. If we have hydrogen, we also have a straight line for our specific heat capacity. Because we heat it up, it gets warmer. The hydrogen atoms, molecules, move around. But at some point we have enough energy that we can activate quantity of rotational momentum, rotational motion. So we start to spin our hydrogen molecules. We couldn't do that with the argon because it doesn't affect it. So then it's going to take more energy per unit temperature to heat up our hydrogen. So this would be rotation activated. And it's not exactly straight up, but we effectively is a step in specific heat capacity, and then it carries on, and then we activate vibration as well. And then we get fairly constant specific heat capacity after that. What's interesting about this is that some of these temperatures are actually accessible. So if we look it up, we can see that it is possible in normal conditions, while actual living humans are in contact with it, to get down below the vibration temperature. And then our specific heat capacity of hydrogen is actually lower, because the energy that we're putting in is all going into, it's going into less thing. It's all going into rotation and translation, and what we measure as temperature is just the translational energy. So if it's all going into the translation, obviously we don't need very much to heat it up by 1 degree. If we divide it into 3 different types of energy, of stores of energy, then 2/3 of it aren't doing the thing that we want it to do. So it takes more heat per unit mass. So the specific heat capacity goes up. So we can actually measure that. It's kind of interesting that it's really happens in normal temperatures. If we stay on our hydrogen, the next most energetic thing that we can do to it is we can kick one of the electrons in the bond into another orbital. So we can change the electron states. We had that with our argon, but I didn't really go into it. So let's describe it here. We've got a bond here with a bonding electron and another bonding electron, and that's not the only place that those electrons can go. There's also an anti-bonding orbital over here, an anti-bonding orbital over here. So if we kick this a little bit, we can kick this electron into an anti-bonding orbital where it sits on the outside. It's not a great diagram for it. Let's draw it better. Well, let's draw it better like this. So this is our anti-bonding orbital, and this is our bonding orbital. The bonding orbital is obviously in between because it holds the two positive cores of the hydrogen together. And the anti-bonding orbital is obviously on the outside because if we put both of the electrons in the anti-bonding orbital, it's actually anti-bonding. It's going to pull those two hydrogens apart. They will actually move away from each other. If we have one in the anti-bonding orbital and one in the bonding orbital, it's quantum mechanically both in this end and in this end. So this one is pulling them apart and this one is pulling them together. And it's touch and go. Unless it falls back down again, they can drift apart from each other. So we can put some of our energy, we're talking about spectroscopy here, so we can put some of our light energy, in this case, into electrons, and they will go into different electronic energy levels. And so that is a different way of getting energy into the system. That requires much higher energies, and that's up in colored light and ultraviolet. So we were in infrared, now we're in colored and ultraviolet, so visible light and ultraviolet. In this case, obviously, hydrogen is not visible. Doesn't appear to be a color if we look at some hydrogen. So obviously this isn't in the visible spectrum, it's in ultraviolet. It takes quite a lot of energy to break a hydrogen bond, but not a super amount. The next most energetic thing that we can do is we can talk to the non-bonding electrons. So we can go into the core electrons here, which would be the 1s electrons of the carbon or the oxygen, and we can knock those into another excited state. So we can do that. We can affect these electrons in here and knock them up into a higher energy level, or the oxygen 1s, we can also do that. So if we do that, we can put some energy in, but we would expect that to be at a very short wavelength, at very high energy. It's outside, ultraviolet is outside our normal experience, but we can still use that to measure things about our carbon dioxide in this case. We want to know, is this carbon, for example? So if we hit this, we can either knock the electron out, or we can excite it and let it fall back down again and measure something. And going back to our hydrogen and going up in energy further, we then have to talk to the nucleus. So we can excite the nucleus. The nucleus can give out particles, but we're getting into outside chemistry mostly. We're getting into a problem that's closer to nuclear physics than it is to chemistry, so we won't do that too much. Let us go all the way down to the other end of where chemistry happens, because we forgot to talk about microwaves. So we deliberately forgot to talk about microwaves because microwaves are not interacting directly with molecules or atoms. First problem with them is that they're far too big to do that. The wavelength of a microwave is of the order of centimeters, typically a few centimeters, but they can be longer than that. So this wouldn't be a surprising wavelength for a microwave. The ones in the microwave oven are typically a few centimeters, 3 centimeters, depending on which one it is. So what do we want to do? Well, or what are they doing more importantly? Well, they are pushing around molecules. What do we know they interact with? If you look it up or you have played with it, what you will know is water gets hot. Ice doesn't get hot very much. So if you have something that's frozen, it does very little and then suddenly it all melts. Butter is a problem. It appears to do nothing and then suddenly melts. and salty water gets hotter than non-salty water if you got them both in at the same time. So what do we learn from that? It must have something to do with charges, and it must be doing something that's bigger than molecules, because the moment that something is liquid and starts to move around, it gets hot very quickly. That's why our butter goes from solid to liquid very quickly, because it's hard to dose the amount of microwaves. It's much more efficient at absorbing microwaves when it's liquid than when it's solid. I'm just wondering whether that's a good thing to talk about. Yeah, let's do that. So what is butter? Butter is a mixture of water and fat, and it's reverse emulsion, so it's fat on the outside, fat is the block, and it's got water droplets in it. The water droplets are a little bit small to be able to absorb a microwave. Microwaves are of the order of centimeters, and if you've heard the urban legend, it's theoretically possible for an insect like an ant to hide in the cold spots of a microwave and not get killed. In reality, it would be very difficult because they don't have a sensor for it, and it's quite powerful and very quick. So it will be difficult for them to find out where to go, but still, it's theoretically possible. If we have our butter, we've got the same problem. We've got a very inefficient coupling of energy into our butter because the microwave has a very long wavelength compared to the size of the droplets of water. When it becomes a puddle, the salt and the water can move around, and it's them moving around in the field of the microwave, being pushed by the microwave passing through it, the microwave photon passing through it. It's them moving around that causes the butter to get hot. Likewise, it is much more effective on charges, so salty water is better than non-salty water, and so that doesn't usually cause a problem, because effectively our microwave is built that we pipe microwave energy into it and we leave it in there. It bounces around on the inside. That's why all of the microwave is metal. There's usually a little microwave window. My one is made of mica, I think, or it's made out of some kind of ceramic. It should be mica, but it probably isn't, or it's mica that's been glued together with something. It's sometimes plastic, and it sometimes looks like a piece of cardboard, but it's actually, it's actually a ceramic. The microwaves come into the oven and they bounce around inside. So the amount of energy goes up and up and up. Obviously, it isn't 100% efficient, so it does get lost, and some of it goes back down and into the microwave generating device, which is bad for it. But still, what it means is that we have a certain amount of regulation because we can't heat our material up faster by changing what it is. But if we're unlucky and we have a meal that we put in there and some parts of it are salty, some parts are not, the salty parts will get hot faster. It's also why if we put something in there like a Pop-Tart or a cheese sandwich or something, parts of it will get very hot and parts of it will not be very warm at all. It's also to do with heat loss, but mostly where does the microwave energy go? It goes into the things that are most liquidy and most charged. So here are most of the types of movement that we can see. I know my screen has gone bad, but we've got translation where it's moving around, and that would be what we would measure for as heat. So that would be what we measure and take the temperature of. We've got rotation, which can only happen if we've got at least 2 atoms in our molecule, so that we can actually tell when it's rotating, but then it becomes a thing. That is quantized. Translation is also quantized, but the levels are very, very close together. Rotation is quantized, so we've now got 2 things rotating. Vibration is our bond vibrating. We can get energy into that from light comparatively easily. It's quite difficult to cause a rotational change with light only, but it's very easy to do a vibration and a rotation at the same time. because this becomes very confusing and there are a lot of things in here, I usually, and I will do this time, I usually don't talk very much about rotation. Other courses that you might see if you're browsing around the internet or looking for, in different ways, looking for a similar material, or you come from somewhere else. Other courses might concentrate on this more. I've decided in this particular course to concentrate more on vibration and electronic translation, excitations. It wasn't the word that I was looking for, but it'll have to do, because it's easy to get confused, and we have a lot of diagrams that look very similar that we will be dealing with. So vibration is what it is, and it can take the form of either the bond stretching, but if we have 3 bonds, so our water molecule, it can do a new thing. So not only can it vibrate by stretching this bond, it can also vibrate by scissoring, like a pair of scissors. So the 2 hydrogens come together and open apart. That's a different vibrational mode, and that can happen too. Obviously, that's another possibility, and it only can happen with 3 or more atoms in our molecule, because if we have 2, the bond doesn't bend, it just sort of rotates around the other one. So that would be a rotation and not a bending. So we've got a new type of vibration that I've just introduced. Then we've got an electronic transition, where we've got an electron somewhere, either in a bond or not in a bond, that we're kicking up. And the ones in the bond are typically the ones with the lowest energy gaps. So it's the easiest to excite them, but it doesn't mean that they're the only ones we can excite. And then as we go further on, we end up talking to the nucleus, but I haven't put them on this diagram, because if we excite the nucleus, it's not directly related to the movement of the atom. So we can't easily get back to translation. As I mentioned, if we have vibration and the molecule is just vibrating and hits another molecule, its energy can easily be converted into translational energy. So if we warm our system up, we're going to be automatically spreading it between these 2. If we shine a light on it and we wait a little bit, the vibrational energy that we put in there will be converted into translational energy, or at least some of it will. Electronic energy is also on here, because if we excite an electron up into a higher electronic state, there is nothing stopping it falling back down again and converting that energy into other types of energy. Whereas the nuclear energy is different, because we've given it to the nucleus, and it's not that easy for the energy in the nucleus to get converted into translational energy. Not directly anyway. So we had our translational energy, which we can directly generate with a microwave, but it's not entirely true, because we're not moving just one atom around, we're moving a group of atoms around, and it's really the viscosity, the loss that's causing it to get warm. So we're not fully directly causing translation, but we can do that easier by just heating it. Rotation, we can cause that by light, but typically we would get a vibration and a rotation at the same time, and we're going to not discuss it so much. Vibration is the main thing. Electronic transitions are also a main thing. Then we will go on to we'll go on to the further electronic transitions, so the ones not in bonds, and then we will mostly run out of things to do on the high energy end. Okay, so I'm going to stop with this diagram. So why was it that I was reluctant to say we can easily put light in and excite some of these things? Well, there's a problem. Quantum mechanics doesn't always allow us to do things directly. We can't always make the transition that we might intend to do without doing something else. And so in this case, there are certain quantum mechanical rules that we will follow accidentally. We are not going to derive them here. Some of them are quite difficult to derive, some of them not so much. We are going to think about them, however, because they are a requirement for doing different types of spectroscopy. So for a last thing for today, we will think about one of these quantum mechanical selection rules. If we want to take an infrared spectrum of some molecules, we would be putting infrared light in and we would measure what comes out. Because in this particular case, we're going to excite them up from the ground state, because vibrational energy levels are usually very close to the lowest one at normal temperatures. We would be able to lose some energy effectively. We can shine broad spectrum, so the equivalent of white light in infrared region through our sample, and some of it won't get through to the other side. But we have to be aware of these quantum mechanical rules, which tell us how likely an event is. So quantum mechanics is all about probability, and one of the problems here is that the probability of this molecule, hydrogen, absorbing an infrared photon and going up a vibrational energy level is very low, because it doesn't follow the quantum mechanical rule that for infrared, if we're putting in an infrared photon, we're exciting a vibrational transition, we would expect that the dipole moment of the molecule will go up or down. It has to change if it absorbs a photon. So in this case, this molecule has no dipole, and this molecule, with an average longer bond length, doesn't have a dipole either, so there is no difference. This is water, it has a dipole, and if we excite it, make both bonds on average a bit longer, then the dipole moment is higher, because the dipole is in this direction. So it's got bigger. So this is allowed, this is not allowed. What that means in reality, because it's quantum mechanics, is the probability of this happening. So we have an interaction between a photon and a molecule. The probability of the energy being absorbed is way higher for the water, so we see a much darker effect. We see as much more of the light is lost. We don't need as much water to cause the same effect. So we do need to bear that in mind. How am I getting to this assumption that the bond length is changing on average? That's the last thing that we're going to do. So this is our molecule again. I should have done this while I had it on the board beforehand, but never mind. We've got our molecule. It starts at the ground state, and we excite it to an excited vibrational state. So this is a stretchy vibrational state. In the ground state, it's going from this position to this position, so its average is here. This is our average radius. In the excited state, it's going from this position to this position, so our average is here, and our average radius has gone up, and it's a function of this curve not being symmetrical. If we had a symmetrical curve, then it would be perfect. That's why a pendulum or a spring pendulum works, because it doesn't matter how high you are oscillating it, it still has the same center point, and it goes through it faster. It still has the same effect. So the average position is always the same. If we have an uneven spring, one that's stiff on the inside and loose on the outside, then that is not going to happen. We end up with it spending more time further away, effectively. As we excite our molecule up in energy levels, the average distance goes up, because the middle of this curve, I haven't drawn it very well, the middle of the curve goes up. It's obviously far less than where the outside is, but it goes up. So we've got effectively a bigger molecule. It's not the only reason why things get bigger when they get warmed up, but it's one of the reasons why things expand when they get hotter, because the bonds are not symmetrical oscillators, and so their average distance goes up. But that's why the dipole moment also goes up, because if we have a bond with a dipole and it gets on average longer, then the dipole moment will go up, because the dipole moment is effectively the charge times the distance. If we've increased the distance, then we've increased the dipole moment. We could, of course, increase the charge, but that is not happening here, not happening in a vibration. What we're really going to do is change the distance. And it's not the actual distance, because this one is also closer. The hotter one is also closer at some of the time, but the average distance is what matters. Okay, that'll do for today. We'll come back some other time.